Just days ago, for the first time in more than 50 years, 4 astronauts flew around the moon and came home. NASA's Artemis II crew splashed down in the Pacific on April 10th, completing the first crewed lunar voyage since Apollo 17 in 1972. The world watched every moment of it. But here is what most of the coverage missed. The moon those 4 people flew past is not the dead, inert rock most people picture. In the years before Artemis II launched, scientists were quietly publishing revisions to one of the most familiar assumptions in all of space science. The moon is not the completely finished world we assumed. What it actually is should change how you think about everything that just happened in the sky this week. For most of human history, the moon meant mystery. It moved the tides, ruled the calendar, and gave civilizations something to navigate by. Then came Apollo. Between 1969 and 1972, 12 human beings walked on its surface, collected roughly 840 pounds of rock, and left behind instruments that would transmit data for years. When the missions ended, the scientific community arrived at a conclusion that felt complete. The moon was geologically dead. Small worlds lose heat faster than large ones. Without a sufficient interior heat source, the processes that drive earthquakes, volcanism, and tectonic movement gradually stop. The moon, roughly 1/4 the diameter of Earth, had apparently run out of geological energy long ago. Its volcanoes had gone quiet more than 1 billion years before. Its surface was ancient and undisturbed. No active geology, no global magnetic field, no atmosphere worth measuring. It was the most studied rock in human history, and it seemed to hold no more surprises. That picture held for decades. Then something began to shift, not one dramatic discovery, but a slow accumulation of data from missions that looked more carefully than any before them. And right now, that scientific shift carries a very particular relevance. The Artemis program has returned humans to lunar vicinity for the first time since 1972. Artemis II, which just completed its mission, sent 4 astronauts around the moon and brought them all home safely. The questions behind that mission, about surface stability, about water distribution, about what the ground beneath future boots is actually doing, have pushed scientists to look again at data they thought they understood. What they found has not been comfortable. To understand why that matters, you first need to understand why the dead moon conclusion became so solid in the first place. It was not careless thinking. It was based on real evidence. The moon formed, roughly 4.5 billion years ago, from the debris of a collision between the early Earth and a Mars-sized body. The impact generated enormous heat. A magma ocean covered most of the surface, gradually cooling and solidifying over hundreds of millions of years. Eruptions flooded large, low-lying basins with lava, creating the dark plains you can see today with the naked eye. Those eruptions slowed and eventually stopped, the last major episodes occurring between 1 and 2 billion years ago. The interior cooled, the crust thickened and stabilized. Without enough heat to drive mantle convection, without tectonic plates to recycle the crust, without a fluid core large enough to sustain a global magnetic field, the moon appeared to settle into permanent silence. The Apollo seismometers seemed to confirm this. They detected activity, yes, but the moon did not shake like a living world. The rocks showed no evidence of recent heating. The conclusion seemed airtight, but the seismic record was more complicated than the summary suggested. Over 8 years of operation, from 1969 to 1977, the Apollo instruments detected thousands of moonquakes. Most were small, deep events occurring at depths of between roughly 700 and 1,200 kilometers, likely driven by tidal forces from Earth pulling on the moon's interior. These were expected. A second category was neither small nor expected. Shallow moonquakes, originating at depths of up to about 200 kilometers, far shallower than the deep events, were in some cases surprisingly energetic, some reaching the equivalent of magnitude 5.5. On a world with no standing structures, that level of ground movement does not topple buildings, but it reshapes terrain. And more importantly, shallow moonquakes require stress. Something near the surface was still generating forces powerful enough to fracture rock. The source of that stress came into focus when NASA's Lunar Reconnaissance Orbiter began returning detailed images of the surface after 2009. What it revealed was a type of feature that earlier surveys had only partially mapped: lobate scarps. These are low, curved cliffs running for kilometers across the landscape, formed when compression breaks the crust and thrusts one section upward over another. They are exactly the kind of feature you would expect on a world that is still slowly contracting, still losing heat, still shrinking, its brittle outer skin cracking as the interior cools. A study published in Nature Geoscience in 2019 examined these scarps alongside the Apollo seismic data and found something significant. Several shallow moonquakes in the original records appeared to have originated near known lobate scarps. And analysis of the scarps themselves showed that some were geologically young, not worn smooth by the slow erosion of micrometeorite, impacts that gradually degrades all lunar features. On the Moon, surface erosion operates on timescales of hundreds of millions of years. Scarps that still look fresh suggest activity, possibly as recently as 100 million years ago, a blink in geological time. The Moon's crust is still fracturing. The residual heat driving this process comes from two sources: heat still slowly dissipating from the Moon's formation, and ongoing radioactive decay within the rock. The geological activity that remains is quiet and slow, but it is real. These are not Earth-like tremors. The moonquakes are slow by seismic standards, with long vibrations that can last for more than 10 minutes, far longer than typical earthquakes. This is because the Moon's interior is dry and rigid compared to Earth's water-saturated rocks, which absorb seismic energy more efficiently. The unusual character of lunar seismic events reflects how different the Moon's interior is and how much more remains to be understood. This is not the same as saying the Moon is geologically vigorous. There are no active volcanoes. There is no plate tectonic system. The total shrinkage since volcanic activity peaked is modest, approximately 50 meters of circumference reduction across a vast span of geological time. But a world that still contracts, still generates seismic events, and still fractures its crust is a world that has not fully settled. And the surface story does not stop there. For most of the 20th century, the Moon was considered completely dry. Then, in 2009, NASA intentionally crashed the L.C. Ross spacecraft into a permanently shadowed crater near the South Pole and analyzed the resulting plume. The result was unambiguous. Water ice exists in the lunar polar regions. Subsequent missions confirmed it repeatedly. In 2020, data from NASA's SOFIA Airborne Infrared Observatory detected water molecules in Clavius crater on the sunlit side of the Moon, not just in cold, permanently shadowed traps near the poles, but in illuminated terrain. The precise form of this surface water is still under investigation, and some aspects of the SOFIA detection have been interpreted cautiously in the literature. But the broader finding is settled. Water is present on the Moon. It is more widely distributed than anyone expected, and it does not sit completely still. Models indicate that water molecules migrate slowly across the surface through a process of thermal desorption and ballistic hopping, gradually accumulating in cold polar traps over geological time. The Moon's surface chemistry is not frozen. It is still, slowly, evolving. Taken together, these findings produce something that the simple dead Moon picture cannot accommodate. A world that still fractures, still quakes, and still redistributes volatile material across its surface is not, by any rigorous definition, completely inert. The difference may seem technical, but it is real. It changes how scientists model the moon's thermal history, how they evaluate the stability of the surface over engineering timescales, and what questions the next generation of missions will need to answer. There is also a broader implication here. The Moon is the most exhaustively studied extraterrestrial body in human history, visited by 12 people, analyzed by more than 140 missions, studied by scientists on every continent for 50 years, and the picture has still changed. Not because earlier scientists were careless, but because the Moon kept revealing more when better instruments looked more carefully. If that is true here, the implication for how much we do not yet understand about other worlds is significant. This is not a minor refinement. It is a scientific correction to a claim that most educated people treat as settled fact. The Moon is dead is one of those statements that has been repeated so often across so many textbooks and science documentaries that questioning it feels almost strange. But that is precisely what careful science is supposed to do. And in this case, the careful look returned a different answer than the familiar one. The crew that just came home from Artemis II flew past a world that geologists now understand differently from the one the Apollo crews described. When the next Artemis astronauts eventually land on the surface, the crust beneath their boots will still be slowly compressing. The ground will still occasionally move. The polar regions hold water ice that has been accumulating for billions of years, and the migration of surface volatiles continues slowly, subtly, but measurably. The surface is not inert. It is quiet in ways that, for decades, were mistaken for finished. The Moon has been above every human civilization that has ever existed. It has been a fixed point in the sky for every scientist who ever looked up. The assumption that we understood it, that it had given up all its secrets, felt reasonable precisely because it felt so thoroughly established. It was not as settled as it seemed. The world you have looked at your entire life turns out to carry a more complicated story than the textbook summary suggested. Its ground still occasionally shifts. Its surface still slowly evolves. And the people who will next walk on it are preparing to study a world that science has not finished understanding. That is not a comfortable conclusion, but it is an honest one. If you found this useful, tapping like and subscribing helps this channel keep going. We really do appreciate it. See you in the next one.